All right, let's talk about something truly wild, something that messes with our whole idea of reality. You know the force that keeps our feet planted on the ground, right? Gravity? Well, it turns out it's also messing with something else we take for granted, the flow of time itself. So let me just throw this out there. Could you live through a couple of minutes while for someone else, somewhere else, years, maybe even decades have just flown by? I know, it sounds like something straight out of a movie. Impossible, right? Well, what if I told you that's exactly how our universe actually works? Yeah, no fantasy here. This is a real thing. It's called gravitational time dilation, and it's a huge part of Einstein's theory of general relativity. And the core idea, it's actually pretty simple when you boil it down. Time isn't constant. It actually runs at different speeds, and it all depends on how strong gravity is. The stronger the gravity, the more time gets stretched out and slowed down. Okay, to really wrap our heads around this, let's forget all the complicated math for a second. Let's just think about it with a simple analogy. All we need are two clocks. They're perfectly identical, perfectly synced up. The only thing that's different is where we're going to put them. So imagine this. We take clock number 1 and put it right here on the surface of the Earth where gravity is doing its thing. Then we take clock number 2 and send it way, way out into space, far away from Earth's gravitational pull. So what happens? Well, the clock out in space, it literally ticks faster than the one down here. It's actually experiencing time at a quicker rate. Meanwhile, our clock on Earth, which is sitting deeper in what physicists call a gravity well, is running just a tiny bit slower. And this isn't a guess, it's measurable. And that right there, that's the fundamental rule. If you take away just one thing from all this, let it be this. The stronger the gravity, the slower time passes. It's that direct. It's a simple, powerful relationship. Okay, so the next logical question is, what controls this? What makes the slowdown bigger or smaller? Is it the same for Earth as it is for, say, Jupiter? And the answer is, nope, not at all. There are basically two main dials that you can turn up or down to change the effect. And those two dials are mass and distance. It's pretty intuitive, actually. First, there's the mass of the object. The more massive something is, like a planet compared to a star or a star compared to a black hole, the more it warps time. It's a bigger gravity well. And second, it's about how close you are to it. The closer you get to that massive thing, the deeper you go into that gravity well, and the more time slows down for you. All right, so this is not just some weird physics thought experiment. This time travel, if you want to call it that, is happening right now all around us. And it happens in ways that are so small you'd never notice, and in ways that are so extreme they'll just blow your mind. Let's start with something you probably use today. I'm talking about GPS. Seriously. The GPS in your phone, in your car, it only works because scientists and engineers account for time dilation. The effect is super, super tiny, but if they ignored it, the whole system would completely fall apart. So here's the deal. Those GPS satellites are orbiting way up high, far above the Earth, and up there, gravity is just a little bit weaker. So what does that mean? It means their clocks are ticking just a little bit faster than our clocks down here on the ground. We're talking about a difference of about 38 microseconds every single day. Now, that sounds like nothing, right? But it adds up. If the system didn't constantly correct for that tiny time difference, your GPS would be off by several miles within 24 hours. It's a perfect real-world example of this stuff in action. Okay, so that's the small-scale stuff. But what happens when we take that mass style and crank it all the way to the max? Well, then we end up at the most extreme places in the universe. We end up at a black hole. And near a black hole, time dilation isn't some tiny little adjustment. Oh no, it is a full-blown reality-bending phenomenon. This is where we get back to that crazy question from the beginning. If you've ever seen the movie Interstellar, you know exactly what I'm talking about. If you were in a ship orbiting close to a massive black hole, the gravity would be so intense that your time would slow to a crawl. You could spend an hour there, and when you get back, everyone you knew could be decades older. Your minutes literally would be their years. So you see, this isn't just some cool, weird fact about the universe. Realizing that time is not constant, well, it fundamentally changes everything we think we know about reality. It forces us to throw out some of our most basic ideas about how the universe is put together. So you might be asking, why does this really matter? I mean, beyond making sure my map app works, why should I care? Because this idea, it hits at the very core of our understanding of, well, everything. Space, time, the whole shebang.
It really boils down to two huge takeaways. The first one, this idea we all have of a single universal now, that it's the same time right now, here and on Mars and in another galaxy, that's just not true. It's an illusion. Time is local. Your now depends entirely on the gravity you're experiencing. And the second big thing is that gravity isn't just some force pulling things down. It is literally bending and warping the fabric of the universe, what we call space-time. It shapes space and it shapes time.
And that's where we'll leave it, with this final thought. If something as basic, as fundamental as time isn't what it seems, if it can be bent and stretched by gravity, it really makes you wonder, doesn't it? What else about our reality is just not what we think it is? What else are we missing about this incredibly strange and awesome universe we live in?